Our next speaker is Simone Milanesi from the university. He's a PhD student at the University of Pavia, and today he will talk about early detection of VSS penetration via funnel plots of regional reproduction numbers. So please, Simone.
Okay. Hi everyone. Thank you to Lorenzo and for the organizers for having me. And thank you also to the audience that you're kind of forced to listen to this. And sorry, here we are. The topic I'm bringing to you today is the early detection of COVID variants of concern by a statistical tool named funnelplot. I structured the presentation into, I would like to structure the presentation into 3 parts. Thank you. Okay. The first one is a disclosure about the topic. The second one, we are going to give the fundamental of this kind of tool. And in the last one, we are going to analyze some cases of interest. So we can start with this first part, funnel plots and control charts. The problem we are trying to tackle is monitoring the performance of institutions or units of analysis of different sizes. This is a very important concept. The problem commonly falls into the area of statistical process control, whose fields of applications are very wide. We've got, for example, healthcare, clinical trials, industrial production, and also university research. For example, the Department of Mathematics in Pavia has recently won the title of the Department of Excellence in Italy, and the analysis was led by a statistical tool of this kind. So, what is a funnel plot? A funnel plot is a statistical tool for comparing institutional performances, where we've got an estimate of a significant quantity plotted against an interpretable measure of its precision. In this example, we've got that each color dot is an institution and refers to an English region. For example, we've got that the green point is the London region, and for example, brown point is the southeast. Control limits, that are these curved lines, are hence introduced to detect anomalies in institutions associated to the estimated quantity. Of course, they give the name to this funnel plot. Okay, more in detail, a funnel plot is composed by 4 elements. The first is indicator Y, that is the index of quality for the chosen institutions. In our example, the indicator is the RT, the reproduction number related to the COVID pandemic. Second, we need a target, theta 0, that specifies the expectation of the indicator. And in our example, we've got that the target is a little above 1. And this is represented by this dotted line. Third, we need a precision parameter, ρ, that determines the accuracy with which the indicator Y is measured. Here we have chosen the active cases. And by precision parameter, we mean that, for example, we trust this orange point far less with respect to this brown point, because the value corresponding to the orange point is computed by starting from a set whose size is smaller with respect to the brown one. And of course, then we need the control limits, YP, that specify if a point is in or out of control, with the constraint that any control point can be outside the control limits with probability P. In our case, P is equal to 0.27%, and we've got that these 2 curved lines divide the plot into 3 areas. One area of natural variability, in which data are assumed to be in statistical control, reasonably around the target. And then we've got the special causes areas in which data are assumed to be out of statistical control. So, for example, if we go to the December 16, 2021, we can see that the London region has escaped the funnel, and we can interpret this thing as a special cause arrived in London, in the London region, and caused the point going out from the control limits. In this sense, a funnel plot has to be interpreted as a homogeneity chart, in the sense that it detects institutions that behave in a different way with respect to other similar institutions. Of course, funnel plots are only diagnostic tools. They reveal the presence of these special causes, but they cannot identify the cause of the anomalies. So further investigation are always required. Okay, our first problem with this tool is that a funnel plot is a photograph of a fixed distance. We have a picture for the 3rd, one for the 10th of December, one for the 16th, and one for the 24th. So a natural question arises, that is, how is it possible to have a dynamic representation of the evolution of the situation? And the answer is positive, by using a control chart. How do we move from the set of pictures to this control chart? The idea is that each date, for example, the December 3rd, goes into a vertical line corresponding to the date. And how do we move these color points into this chart? The answer is pretty simple, by normalizing them. That is, we translate the target to 0, and we rescale the control limits such that they become this horizontal line. So, of course, we have gained something. We've got a dynamic representation of our phenomena, but at the same time, we are losing something else. For example, if we compare the values of the green line at the 3rd of December and at the December 24, that are the first and the last picture, we can see that in the first case, the RT is around 1, and in the second case, it is around 1/12. So in the second case, for example, a lockdown is needed, while in the first case, the situation is more relaxed. The control chart doesn't discriminate between these two situations. Of course, we can see that the values that the line is assuming are the same. So it is important to have both of these tools together. One for evaluating, to assess the gravity of the situation, and the other to have this dynamic representation. Okay, so where can we use these tools? The examples are a lot. For example, quality control in industries, meta-analysis in pharmaceuticals field, and then offshore, oops, my fault. I meant monitoring university research activities. Here we can see that Pavia has won the title of Department of Excellence thanks to a funnel plot. And we can see that Pavia hasn't the highest VQR score. For example, there is this institution there. But thanks to the sample size that is rated to the number of researchers in the department, it was considered better with respect to this one. Then we've got comparing hospital performances. That is also one that was brought into light by Spiegelhalter, the one who introduced these kind of tools. Finding serial killers. That is a 100% clickbait title, because around this time people begin to get bored, so we have to press their attention. Actually, it's a fun story. If we want, we can go back at the end. Finding irregularities in collective data. And at the end, finally, the reason why we are all here, that is the detection of a variant of concern. Here we've got that the Independent on December 13th wrote, Omicron said to be dominant coronavirus strain in London by Tuesday. And I want to stress that our tool has been detected the anomaly around the December 5th. Okay, disclosure ended. We can go to the fundamentals of this tool. As I already said, the indicator has to be a significant parameter with respect to the analyzed field. In our case, we want to detect COVID variants of concern, and so it is appropriate to choose the RT as our indicator. First question, how to obtain a probabilistic model of the RT variability across regions? And concerning the precision parameter, common choice is the size of the set on which the indicator has been estimated. In our case, we want to choose the number of active cases that is easily interpretable, and so there is a natural second question, that is, how do we calculate the RT by starting from the active cases? Actually, we can start from the second question, and then we skip the calculation because of time, and also because this formula is a very well-known formula, known as the Corey's formula. That is the one adopted by, for example, civil protection or the ISS, that is the Istituto Superiore di Sanità in Italy. And the RT is estimated with this fraction. At the denominator, we have the new positives. At the denominator, we've got a discrete convolution between these discrete coefficients, WS, and the new positives. The P are in free download. You can download them from a lot of websites, for example, the civil protection site or a worldometer. the WS has to be interpreted as the time profile of the infectiousness of the individuals. And this denominator is related to the active cases thanks to a constant related to the removal rate of the COVID phenomena. For the choice of W, different sources use different choices. It has to respect some prejudice that the author has on the infectivity profile. And common choices are a log normale, or a gamma, or a negative exponential. For example, in this work, we have chosen to have a log normale, according to some papers. Okay, concerning the first question, that was how can we obtain a probabilistic model of the RT variability across regions? That is far more interesting. We've got that before describing the target and the control limits, it is appropriate to introduce a probabilistic frame. It naturally follows the SIR model, that for us is the Goris formula, by imposing x equal to the discrete convolution, that was the denominator for a sake of notation. We can think about the new positives as a Poisson random variable with mean RT times x, so that P is a random Poisson of mean RT times x. It is well known that if the parameter of the Poisson is at least 1000, and you know some sources all said also at least 30, so we are in good hands, the distribution can be approximated by a normal distribution, so that we obtain P as a normal of mean RTX and the variance RTX. So we can define a new random variable, RT bar, that has to be interpreted as a regional RT, defined as P over X. This is a linear transformation of a Gaussian, and so we obtain that RT bar is a normal of mean RT and variance RT over X. In this stochastic frame, we can reformulate the problem of finding the target and the analytical form of the control limits. And in homogeneity context, the regional RTs are assumed to be normal random variable with the same mean. This is very important. Hence, we can estimate the target in the following way. This is a weighted sum. RT is the theta zero we have introduced before, RT hat. And this is a weighted mean where the beta I are the coefficients, the weights, related to the number of active cases in the region we are considering. And the RTI bar hat are the RT computed thanks to the Goris formula that we have introduced before. Okay, so now we've got everything except for the control limits. But thanks to the assumption of normal distribution for the indicator, the analytical form of the control limits is the following one that you can see here. And in our case, we obtain that y 0.27% over n is equal to RT bar, the weighted mean, plus or minus ZP for this quantity. I want to stress two things about this formula. The first is that we've got the active cases here, as we wanted. And the second is that here we've got an over n because of the Gonferroni correction. That is a common correction when we are performing multiple testing, as in this case, where n is the number of regions we are analyzing. Okay, so it looks we've got everything, but actually a problem can arise when a performance indicator shows substantially more variability than would be expected by the ideal model. For example, here there is a picture taken from a Spiegel author paper, in which we can see that there are a lot of institutions out of control, both over the mean and under the mean. We don't like a situation of this kind, and so to correct this anomalous behavior, we can say we can introduce a multiplicative over dispersion parameter, whose aim is to avoid, have more larger limits and avoid this kind of situation. In our case, all these objects, that is the variance of our y, of our indicator, has been estimated starting from the data at disposal. Okay, now we got everything we need for a situation of homogeneity. With, by starting only with the new positives data, we can construct this plot. But what happens when an institution disrupts the balance? In this case, the green point has escaped the funnel. Is it correct to use such a region in the estimation process? Of course, no. We don't like this kind of behavior. The real algorithm has 5 steps. The first, all regions are supposed to be in control. The Second, mean and variance are calculated on the basis of in-control region. Then the final plot is drawn, and out-of-control regions are detected. If there are any, we go back to the second point and we repeat the algorithm by using only the in-control points. If there aren't, the final plot is displayed. In this sense, the final target and the control limits depend only on the regions that are inside the in-control area. Okay, so we can go to the last part. It is the analysis of some cases of interest. Here, there is, I think, the most impressive result. We have analyzed in a situation for 18 months straight, from December 2020 to May 2022. And we can see that a lot of main events reported by national press, for example, have been detected by this method. We've got the, for example, concerning the variants of concern, the emergence of alpha variant in A. In C, we've got the arrival of delta variant. In E, we've got the arrival of Omicron variant. Okay. Another example is the emergence of delta variant in India, and also the emergence of Omicron variant in South Africa. So, to conclude, I've got a little video that I have to find on this computer. Okay, the video refers to the English situation in those 18 months, and it is another way to visualize in a dynamical way the situation. It is an alternative to contour charts, and it is obtained by putting one funnel plot next to other. And as you can see, there is a typical behavior of these dancing points. They do clockwise trajectories, and it is quite natural because of when the RT rises, the infectious cases rises as well until a plateau when there is a lockdown or there is a saturation, and with the plateau, the infectious cases start to slower, and the RT gets lower as well. Okay, and it has started again. With this, I have concluded. So, thank you for your attention.
Thank you, Simone, for your presentation. Is there any question? Okay, I have a little question. Did you observe like similar behaviors in the trajectories for other analysis, or this is the only analysis you performed?
This is the only analysis I performed, but I think it is quite a natural behavior when we are going to analyze a phenomenon in which there is a plateau, in which there is the indicator that grows as the parameter precision parameter does until a plateau due to a saturation.
Okay. So you expect to in this situation always see
in epidemiological context, yeah, there are.
Clockwise.
It was something that was observed also in other papers in other contexts.
Okay.
I forgot about it. So about the assumption of Gaussianity of data, it's something that is easy to check, or
we have performed some tests, the number of tests with epidemic, and it was confirmed.
in case you have a different distribution, maybe you can find different laws for the...
Yeah, that's right.
Any other question?
A small curiosity, similar to the question about the trajectories. But is it related, for instance, is it similar to the behavior of trajectories, for instance, in lockable Terra models, or is quite a different phenomenon?
I actually think it is quite different, but it's something that I'm not an expert of. So.
Any other question? So just last quick question. Could you tell us something more about the serial killer case?
It is a clickbait title because the funnel plot was performed after he was arrested, so he wasn't caught with a funnel plot. But there was this physician named Shipman who killed grannies. And so someone noticed, and he was arrested. And after the arrest, a funnel plot was displayed where the indicator was the mortality of the patients, and the precision parameter was the number of patients for physician, and the point of shipment was outside the funnel. So it was a posterior analysis.
It was cheating because you know the game.
Yeah.
Okay, so if there is another question, let's thank again the speaker.